In this video, we're going to look at refraction for GCSE science. So the first thing that, of course, we need to be aware of is the definition of refraction. And I think that's best summarized as when light changes medium. Now, medium is a fancy word for material or substance. So, for example, light, air, glass. It changes speed and direction. All right, that's the most basic idea that we really want to ram home to students, because if they can memorize this, there's a good chance they can remember a lot of other things that are going on. So refraction is something that happens with all waves. All right, it doesn't matter whether they're sound, light, seismic waves, they will all refract. However, we're going to talk about it exclusively to do with the light, because that's what comes up at GCSE. There are some really nice videos online of people doing things like making lenses for sound out of carbon dioxide balloons. And you can talk about things like, if there's a music festival going on and there's some houses really far away, people will hear the music festival really far away because the sound refracts, changes direction in the layers of the atmosphere when the air changes density. All nice extension stuff, but we're going to focus purely on the light stuff. So let's look at the most common kind of picture. So we're going to have a glass block, and then there's going to be air on either side. So we will have some light coming in to this glass block, and we want to decide what's going to happen. So the first thing we always need to do, and it's really important to make sure students do this and understand what they are doing, is to draw on the normal line. The normal is the line at 90 degrees to the surface. Students may well ask, where do I draw the normal? Why don't I draw it over here? Why don't I draw it over here? Well, it's where the light hits the surface, hits the object. So now we need to decide what's going on. So here we're going from air to glass. So we're going from less dense to more dense. So when something goes from less dense to more dense, what does it do? It slows down and it bends towards the normal. All right, so really simple. We've really simplified this as much as we possibly can. So now on our diagram, we can draw it bending towards the normal, so towards this way, the normal. Now when it's going from glass to air, what's going to happen? So now it's going from more dense to less dense. So it's going to speed up and it's going to bend away from the normal. So just like before, we need to make sure we draw on the normal at 90 degrees. Now it's going to bend away from the normal. So it's going to bend this way, away from the normal. And actually, this line and this line should be parallel to each other because they've started in air. So they're going to be traveling in the same direction. So at this point, students might say, how much does it bend towards or away from the normal? So you can either say that doesn't really matter, or you can say that it is an A-level topic, but if you want to work it out, then you can use this formula here. I would probably only show this to the most able students. I might show it to less able students, and then they probably would stop asking me questions. This is known as Schnell's law. Okay, and it relates the angle of incidence to the angle of refraction, so how much it bends, to the two refractive indices. So n is the refractive index, and this is a measure of how much a material or a medium refracts light. It's actually just a really simple ratio. So if you measure the speed of light in glass and the speed of light in air, all n is telling you is it's telling you the ratio of the two speeds. Right, so it's actually really quite a simple concept. But like I said, this is A level, so it's not something to worry about too much. All right. Now, of course, we need to know what these angles actually are and what they mean. So let's look at another very important diagram. So here again, let's say we've got air and we've got glass. So we know what's going to happen. The light ray is going to come in. We're going to draw our normal at 90 degrees, and it's going to bend towards the normal. And we should always put arrows on just to show which way it's going, just because it's quite helpful. So we need to label this angle here. This is the angle of incidence. It's the angle between the normal and the light ray. And this angle here is the angle of refraction. And again, it's between the normal and the light ray. Students very often label these angles, which is not the correct angle. One other kind of exception or interesting case, if the light ray is actually coming in at 90 degrees, what's going to happen? Well, it will slow down, or it will change speed. It could speed up if it's going to a less dense material, but it won't change angle. Obviously, it cannot bend towards or away from the normal because it is at the normal here. So it'll just continue straight through. I should probably say at this point, or I should have said at the start, we should always use a ruler for drawing these. Okay, when students do this in the exam, they should use a ruler and they should use pencil as well, in case they make a mistake or they want to change it. So all of these diagrams, not perfect from an exam point of view. Let's look at a couple of other interesting cases. So you may well get, a surface like this that's curved. So let's put air here and glass here. Although of course it could be the other way around. And we just really need to use our common sense now. So the light ray is coming in. We need to draw our normal at 90 degrees to the surface. We need to use this basic idea here. It's going from more dense to less dense. It's going to speed up. It's going to bend away from the normal. So it's going to go away from the normal this way. Drawing these arrows on can actually be quite useful for students as well to understand which way you mean. So away from the normal. And now what's going to happen? So we need to draw on our normal again. And it's going from less dense to more dense. So it's going to slow down. It's going to bend towards the normal. So it should be going this way, but it's going to bend towards the normal this way. So it's going to come out over here somewhere. All right, they could give you curved shapes. They could obviously switch around the two materials. As long as you follow the sequence of steps, you're able to do it every single time. One more special case, or not special case, but kind of harder example, and then we'll look at a couple of models. So let's go air, let's go glass, and then finally, let's say that we're going into water. So they could well give you multiple materials. So here, same sequence of steps. What's going to happen? Glass is more dense than air, bends towards the normal. And now we've got water and glass. Water is less dense than glass. It's going to bend away from the normal. And because these aren't the same materials, they're going to have different refractive indices. These won't strictly be parallel. But usually these diagrams at GCSE are not to scale. The materials that most commonly come up, air, glass, water, and oil, because obviously the density of oil is obviously noticeably different to water. And of course, when we're talking about water, we do get some really nice sort of optical illusions, right? The really common one, you've got a glass of water and we've got like a straw that's in it, and the straw appears to be broken or appears to sort of jump, right? Again, because of refraction. Really easy to demonstrate in a class. There's also a really nice other similar thing you can do if you get a glass of water, and if you put behind it, you put two arrows, and then as you fill up the water, the arrow will change the way it's pointing, again, because of refraction. You just got to be careful that the spacing of the glass to the arrows is correct. If the glass is too close or too far away, we don't see this because we get other effects due to lensing. So a little bit of practice will be required. There's also some nice GIFs for this. Now, we need to be aware of two other things for refraction. We need to be aware of a couple of models that we can use, and then one other way of drawing these diagrams. So the most common model that's used is you have something like a car, or it could be a column of people, and the car is moving towards a patch of mud from a patch of concrete. And then what happens to the speed as it goes through mud? Obviously, it slows down. And then as the car actually hits the mud, what do we notice? Well, because it's at an angle, this wheel hits it first. So this wheel now travels slower. So this wheel will only get to here in some amount of time, whereas this wheel will travel faster. So it'll be able to get all the way over here. So now we've actually rotated the direction of the car. All right, and then obviously the car gets to here, and this wheel hits the new patch of concrete faster. So this wheel now starts to speed up, and again the car rotates round this way. This is much clearer with like a GIF or an animation rather than just a diagram like this, but that's the most common explanation. Perfectly fine, nothing wrong with that at all. Students usually get the idea that obviously as soon as a wheel hits mud, the whole thing will swivel around. The other example that I quite like to use, potentially because if you really want a fuller explanation of refraction, you need to look at some relatively complicated maths, and this model is potentially slightly better for it. We have a person, and they're trying to get to the other side of a river, and then I usually make it somewhat dramatic by saying something like there's a burning puppy, or a puppy in a house that's on fire, just because that usually makes students remember that. What's the quickest way that you can get to the building? So you obviously run faster than you swim, so it actually makes sense for you to run at this angle and then swim at this angle and then speed up again when you get out, and this is the shortest path in time. You could try to do this, but you've got a very, very long way to swim, and you're going to be a lot slower. Equally, you could try and run completely straight and swim completely straight, but again, you have to swim quite a long way, and that's going to slow you down. This black path is the shortest path, the shortest distance. Of course, students will then say, how does light know this? And of course, light doesn't know this, and the explanation is more complicated. But if you use both of these models together, usually students can sort of pick the kind of easy to understand bits from both of them and get this into their heads. So the last thing I want to talk about is one other way of drawing these diagrams. We need to be able to draw wave front diagrams. So here we're going to again have air and we're going to have glass. But instead of having our wave come in and change angle like this, we're not going to represent our wave as a straight line this time. We're going to pretend it's like a water wave and we're looking down at it. I say water wave because this usually makes it clearer to students what I'm going on about. If I say light wave, they get a bit confused at first. So wavefront diagrams are diagrams where we're looking at the crests of the waves from above. So the wave, although it's moving this way, we have to draw the wave fronts at 90 degrees. This is important. They have to be at 90 degrees. So now when it changes direction, what's going to happen? Well, we again draw our wave fronts at 90 degrees, and you'll see very clearly that it's changed direction. Okay. So it obviously gets a little bit confusing here. I would encourage you to get students to draw on in a different color the way the wave is going, and then they can draw the wavefronts at 90 degrees. If you just start with the wavefronts, students get quite confused by this. So we can draw a diagram like this to really show students what we mean. So we have the wave direction, and we have the wave fronts, and they're at 90 degrees to the wave direction. And then what you can do is you can say, well, pretend it's water waves. We're going to be looking at each peak or each crest of the water wave as if we're looking above, and then we can match up these points. If you've shown students the ripple tank, it makes a lot more sense. Or if you haven't, show them, a picture of a water wave from above, and it makes a lot more sense. You might notice here that the spacing of these wave fronts are slightly greater than these wave fronts. Okay, it's a bit messy, but that was the intention, because if we're being 100% correct, what happens to our wave? Well, we know that the wave speed is frequency times wavelength. For reasons I won't go into, the frequency stays constant, but as we've already discussed, the speed slows down. So if this stays constant, what must happen to the wavelength? The wavelength must also go down. And then if we were to go back into a less dense material, the wave speed speeds up, the wavelength increases, the frequency stays constant. Right. It's not impossible to understand, just a little bit beyond GCSE, so I'm not going to go into it here.